In the last video, we looked at specific heat capacity and heat capacity. And in this video, we're going to look at latent heat and specific latent heat. Now, we couldn't really do any questions after the last question because you kind of need to cover this before you get on to the trickier questions. So, latent heat. I want you to imagine you have an ice cube. And that ice cube is at a temperature of minus 10 degrees Celsius. And you're going to heat up this ice cube, so you're going to get a Bunsen burner and you're going to heat it up. And you're going to supply a constant heat force, so you're always supplying, the Bunsen burner is always at the same setting. Well, let's say you recorded the temperature of that ice cube every 5 seconds. And you kept doing this until all of that ice turned to steam. So let's say I did a graph then of temperature against time. Temperature degrees Celsius, time in seconds. So our initial temperature is minus 10. So if you were to kind of guess what this graph would look like, I'm assuming you're going to guess the temperature is going to increase over time gradually. And you're more or less correct. But there's a couple of little catches if you actually did this experiment. So we have minus 10, that should be temperature. The graph would start to increase. You heat it up, it gets to minus 9, minus 8, minus 7, 6, 5, 4, 3, 2, 1, 0. And at 0, something happens. The graph flattens out. And what you get is, even though you're still heating up the ice, even though you're heating it up and supplying it with energy, the temperature doesn't change. So you're still giving it energy, but the temperature is not changing. So what's happening? What's happening at 0 degrees Celsius? Well, the energy you're supplying is going to break the bonds. You know the ice is basically water in solid form. And solid, the particles are arranged like this. And the bonds between the particles are fairly tight. So what you're doing is you're using the energy, the heat energy that's being supplied to break those bonds. Once those bonds are broken, it's now water. So now you keep heating it up and that water will increase in temperature, go to 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50 degrees and so on, until you get to 100 degrees Celsius. And at 100 degrees Celsius, what you're going to find is exactly the same thing. The energy that you're supplying doesn't cause the temperature to rise, but what it does do is it breaks the bonds. And now the liquid, and you know liquid particles are kind of arranged like this, very close together, touching but not in neat rows, is being used to break those bonds and change the water into steam. And then if somehow you could capture that steam and keep heating it up, you can heat up steam. Steam can be hotter than 100 degrees, 110, 120 and so on. So these two sections here are the sections that we're looking at today. And the energy you supply, here is known as the latent heat. Now latent heat is basically the energy you supply, the energy given. Energy given or required to change the state without changing the temperature. And that's the important thing. It's changing state without changing temperature. And you'll definitely need to remember that without changing temperature when we do some questions. So here we have two sections where there's latent heat being supplied. When we're dealing with ice to water or water to ice, we call it latent heat of fusion. And when we're dealing with water to steam or steam to water, we call it latent heat of vaporization. So the definitions that you need to learn are on page 105 and 106 of your textbook. So the first one you need to learn, and sorry that's a little bit small, but you can pause the video and have a look. The latent heat of a substance is the heat energy required to change its state without changing its temperature, and the unit is joules. So it's on page 106. And what that means, if a block of ice had a latent heat L of 50 joules, it means to change all of that ice to water, it takes 50 joules of energy. Now just like with heat capacity, we have to kind of standardize it a bit. And how we standardize it is we use specific latent heat instead of latent heat. And the specific latent heat is the amount of heat required to change 1 kg of the substance. So that's a much better way of kind of giving the information. So rather than just a block of ice, what we have is we have 1 kg of ice. And we know that the specific latent heat might be, I don't know, 25 joules. And because you know that it's 25 joules for 1 kg, you can scale it up then, and you could say, well, for 2 kg, how much energy would I need? For 3 kg, how much energy would I need? And so on. Now, as I said, there's different latent heats or different amounts of energy is required depending on whether you're going from ice to water or water to steam, because you're breaking different strength bonds. The bonds are stronger in ice than they are in water. So this is broken down further. And we have the specific latent heat of vaporization of a substance is the amount of energy required to change 1 kg of the substance from liquid to a gas. Whereas the specific latent heat of fusion of a substance is the amount of heat required to change 1 kg of the substance from a solid to a liquid. You must learn those definitions. They're really, really common. You need to learn them. Now, it's different for different substances. So I'm talking about ice and water today. And for specific latent heat, the specific latent heat of fusion of ice, this one, and we write that as small LF, is equal to 3.3 times 10 to the 5 joules per kilogram. So what does that mean? That means for every 1 kg of ice, you need 3.3 times 10 to the power 5 joules to change it to water. Whereas the specific latent heat of fusion, small l with a, or of vaporization, small l with a v, is 2.3 times 10 to the 6 joules per kilogram. So because we're dealing with vaporization here, that means if you had 1 kg of water and you want to turn that water into steam, you would need 2.3 times 10 to the power 6 joules for every kg. So this gives us an equation, and the equation is a nice simple one. It's Q, the amount of energy required, is equal to the mass of a substance times L. Now that L varies depending on whether you're going from ice to water or water to ice. So an example might be, let's say you have 5 kilograms of water at 0 degrees Celsius, and you want to change it to 5 kilograms of ice at 0 degrees Celsius. Now notice there's no temperature change, because if we're changing the temperature, there's a different, you're adding more energy as well, and I'll talk about that a little bit more in the next video. So if we want to figure out how much energy is required, how much energy is required to do this, how much energy, that's where this equation comes in. The amount of energy, Q, is equal to the mass, which is 5, times the specific latent heat. Now you just have to make sure you pick the correct specific latent heat. So this is water to ice. So for water to ice, we're looking at fusion of ice. So our L is LF in this case, which was 3.3 times 10 to the power 5. And you can type that into your calculator. What is it? 16.5, I think, times 10 to the power 5 joules. That's how much energy you'd need. Now, if I change that question and I said 5 kilograms of steam to water, I wouldn't use LF, I'd use LV. So the specific latent heat, the specific latent heat of vaporization would be 2.3 times 10 to the power 6. And remember, these values are just for ice and water. If we were figuring out how to change copper, solid copper, to melt it down into liquid copper, we'd obviously have a different value there. But they'll give you those values in the questions, but we're usually dealing with ice and water.